calculus. That's what D&E stands for, does not exist. So if we try to see what the function really does on this graph at x equals 3, we see that we're left with some undefined value. Okay, but we as humans, we can just look at this graph and we can tell, hey, this graph really wants to go to y equals 5. Like say we start from the right and we move towards x equals 3, well, yeah, we get closer and closer to y equals 5. If we start from the left, same thing, we get closer and closer to y equals 5. So even though the function isn't defined to be 5 at x equals 3, we can see as humans, just looking at this graph, that this graph really wants to go to y equals 5. So there's actually a mathematical way to do this, and that's what the limit is all about. So what a limit really tells you, say we have this limit, the limit as x approaches 3 of the function that we're looking at above. So what this is asking us, okay, the limit as x approaches 3. X approaching 3, really, it's asking whatever function this is. I'm not at that part yet, but whatever function this is, we're going to be asking what does that function look like it's going to do at x equals 3. And then here, well, we can already directly see it's 5, but we haven't really gotten to the part where this tells us the function that we're looking at. That's pretty obvious. I'm sure you could have gotten that. But now, answering this limit question just becomes a question of what does this function look like it's going to do? Well, we see at x equals 3, it really approaches 5. That's the key word here, approaches. We don't really care about what the function actually does. It could, well, I'll save that for the next example. Actually, I was going to say something. But, okay, we see limit as x approaches 3. It gets closer and closer to 5 regardless of the direction we come from. So that means that the limit should equal 5. So let's say we have another example, another arbitrary graph. I'm not really labeling the axes, it doesn't really matter all that much. Have a hole very similar to the previous graph, except that this time, function is actually defined at where the hole is. So let's say this is x equals 4. The hole is round at y equals, let's say 9, and then the hole itself is at y equals 13, I'm sorry. So this is the function f of x. So now I ask you, f of 4, well, what should that be? Give you some time to think about that. Okay, well, remember, a function value, whenever we plug in an x to a function, the function value is actually what the function is at that point. So it would just be what the function is defined to be. That's where the shaded hole is. Not really a hole, it's shaded. But this means that the function value is 13, right? Because that's what the actual definition of f of x tells us. But if we look at this graph, we see, no, it really doesn't want it to be at 13. You start from the left, you kind of go toward x equals 4. It doesn't, the function really doesn't look like it wants to go to 13. It's kind of like it's being forced to just jump instantaneously all the way to 13. But also, if we come from the right, just to clarify, exact same conclusion. But if we use the power of calculus, the power of limits, we take the limit as x approaches 4, well, we can actually deduce, what the function looks like it's going to do at that x value. So if we take the limit for that function, well, we see it's what the function wants to do at that x value, regardless of what it's actually defined to be. So that's going to be 9. Okay, so we see that if we have a hole, but the function doesn't have a definition, function value is undefined, yet the limit continues to be defined, okay? We can have a hole and some kind of jump in the definition. The definition exists, the limit also exists, but it's not actually what the function value is. Remember, the limit only cares about what the function looks like it's going to do. Okay, last example, say we have something like this. This one's gonna maybe hit you a little bit harder because it's too simple. This is f of x, okay? This is, let's say, x equals 7. Let's say this is y equals, let's say, 15, okay? So if I ask you, what is f of 7? It's pretty simple. Now I'm going to give you time to think about it. That's 15. And then now if I ask you, well, what's the limit as x approaches 7 of this function? Well, remember, limit is asking you what does the function look like it's going to do as you approach this. So let's kind of check it out. So as we approach it from the right side, well, it looks like it's going to be at y equals 15, okay? From the right side, left side, okay, looks like it's approaching from the left side to be 15. Okay, so we see here that there are actually occasions that the function value is equal to the limit. So limit doesn't really necessarily mean that you have to have a hole. Those that was just used for the examples previously. That's not a necessity for limits. So limits can go on any function. You could have the limit as, here, I'll actually write this down here, that way you don't mix up the notes space. So let's say we have, we'll do the limit as x approaches, let's say pi of sine of x. Okay, well, sine of x, we know that it's defined for all values, so we don't have any holes, we don't have any asymptotes, and we'll actually get to that later in a later video. So it really just becomes as simple as just plugging in the value. We know that there's no jump anywhere, there's no hole, so it's safe. It really is just safe to plug in this value. So sine of pi, or this limit becomes sine of pi. So sine of pi we all know to be 0. Okay, so we see sometimes the limit, it doesn't really change anything about the answer if you apply a limit to a function. Sometimes if the function is defined at that point to be what it actually looks like it's going to do, then, well, limit and the function value are equal. And actually, you'll see in a later video that this is a very crucial step for a function to be continuous, but don't worry about that right now.